Today I'm answering from May 2020 the Physics IGCSE EDEXCEL paper 1P. If you've been following me for a while, you'll remember that at the start of the paper I recommend you write as many different formula triangles as you can. It's worth putting in that time, so you've got your own equation sheet to refer to. I probably won't remember them all. We play tennis, so work done is power times time. Speed equals distance over time. Ke equals half mv squared. Gravitational potential energy equals mass times gravity times height. PIV, so power equals current times voltage. Work done is force times distance. VIR, so voltage is current times resistance. Charge equals current times time. I've just realised they give you that one, but oh well. I'm fine that I've included it again. Force is area times pressure. Density is mass over volume. This question is about wave behaviour. The boxes give 3 types of wave behaviour and the diagrams give 3 examples of wave behaviour. Draw one straight line from each wave behaviour to the example that best shows that behaviour. Okay, total internal reflection, as the name suggests. Reflection, so it's bouncing, and it's internal, so it's all taking place within, which is why it's this one here. Refraction, remember that's when the wave changes speed when it enters a new medium. So we can see here that the wave's slowed down, which is why it's that one. And then reflection is basic bouncing, which is that one there. State 2 properties that all waves have in common. If you've watched my video or bought my revision guides, you know that they transfer energy and they can all be reflected, refracted and diffracted. This question is about the movement of a train. The diagram shows the train on a track. The train starts braking at point P and stops moving at point Q. The graph shows how the train's velocity changes with time as the train travels from P to Q. Calculate the acceleration of the train. So remember, acceleration is final speed minus initial speed over time. So what's our final speed? Well, that's 0. Our initial speed up here is 45, and that took place over a time period of 39 seconds. So do minus 45 divided by 39 to get to 3 significant figures, minus 1.15. Notice it's a minus because obviously the train's slowing down. Calculate the distance travelled by the train from P to Q. Well, it's a velocity time graph, so distance is found by the area under the graph line. So I'm just going to do that up here. So because it's a triangle, we do half times the height, which is 45, there, times the base, which is 39. Pop that into your calculator, get 878 as your distance. And remember, look, I've got my working there. Draw a line on the graph to show how the train's velocity will change if its initial velocity is the same but the braking force is lower. Well, that means it will decelerate slower, so that will be a shallower gradient. This question is about stars. Describe the stages in the evolution of a star similar in mass to the Sun. So that means we're talking about a small star. So remember that a star starts life as a nebula and then becomes a protostar. And then this small star enters the main part of its life, which remember is called the main sequence. And then what happens when it runs out of hydrogen fuel? The star expands to become a red giant, followed by a white dwarf and then a black dwarf. The process of energy release in the core of a star is different to the process of energy release in a nuclear reactor. In a power station, describe how the process of energy release are different. Okay, well we have 2 completely different reactions here. The star, remember, is nuclear fusion, so the fusing of nuclei. In a nuclear reactor, you've got nuclear fission, which is the splitting of the nuclei. So in a star, nuclear fusion takes place. which is the joining of nuclei. In a nuclear reactor, nuclear fission takes place. And if you're feeling fancy, you can name what type of element has its nuclei split, such as uranium or plutonium. State Hooke's law. Remember, this is all to do with hanging weights off a spring and the fact that the extension on the spring is proportional to the load added. But remember, that can only occur to a specific mass, which will vary based on the spring, and after that point the spring will stretch and not go back to its original size, which means it's reached the limit of proportionality, or reached its elastic limit. The graph shows how the extension of a rubber band varies with the force applied. Explain how the graph shows that the rubber band does not obey Hooke's law. So based on what we were just talking about, you'd expect a directly proportional relationship before that elastic limit is reached, and then it goes funny. So let's point out the difference then between these two graph lines. The rubber band's graph is not straight. And what does that indicate? Well, it means that extension and force are not proportional, so it can't be obeying Hooke's law. Diagram 1 shows the model aeroplane powered by a rubber band. A person rotates the propeller of the model aeroplane, which twists the rubber band. He then releases the propeller and it spins. Energy transfer occurs during this process. The box lists words associated with energy. Use words from the box to complete the passage. The person does something work to twist the rubber band. Now the first answer here is mechanical energy. As the person twists the rubber band, it extends, increasing the... Now this is a rubber band, which means it's very elastic. So when you twist it, you're going to increase the elastic store of energy. When the rubber band is released, it does mechanical work, increasing the something energy store of the propeller. You've got two options here, either kinetic or gravitational. Remember, kinetic is all to do with movement. Gravitational is just because it's at height. Diagram 2 shows the aeroplane flying horizontally to the right. The aeroplane flies at a constant speed. Diagram 2 shows two forces acting on the aeroplane. Draw labelled arrows on diagram 2 to show two more forces acting on the aeroplane. So remember that the plane is flying horizontally, so we've got to say here, because it's not going up or down, that the lift and therefore the force acting downwards, which remember is weight, must be around equal. So make sure those lines are approximately equal, which I don't think that is. Better. Now, as the aeroplane flies in this direction, remember there's a force acting against that due to air particles hitting the plane to slow it down its motion. Now that force is known as either drag or air resistance. We've been told here that it's flying at constant speed, so it's not accelerating. So we need to make that arrow approximately the same length as the thrust one and call it drag. The student does an investigation to determine the current voltage graph for an unknown component X. The student uses this equipment. Complete the circuit diagram to show how the student should set up this equipment for her investigation. Oh wow, you've given us so much here. Okay, so we need a cell, so I'm going to put that in its usual position, which is around here. Then in series we're going to add a variable resistor, which remember looks like a rectangle with an arrow going through it, and I'm going to tick them off. The ammeter, remember, occurs in series as well, so that's going to be part of the main circuit. Because we're interested in a voltage current graph for component X, when we add the voltmeter, which we know needs to be added in parallel, it needs to be around component X, like this. And then we just complete the circuit. With those connecting wires that we're allowed to add. The student completes her investigation. The table shows her results. Plot a graph of the student's results on the grid. Plot current on the y-axis and voltage on the x-axis. Draw a curve of best fit. So here's our y-axis, which is current. Now in terms of our units, current we can see from the table here is MA. Voltage is just volts, so capital V. we're going from 0 to 140 for current, so let's check our axes here. So let's go up in 20s. Remember, you want to use as much of the graph paper as possible. And the more you draw graphs, the easier you'll find it to just pluck those scales out of thin air. And then in terms of voltage, we're going from 0 to 0.8. So let's go up in 0.2s. Now we're ready to draw our graph. So you need to stop the video and have a look at those numbers. The first point is 0 on the voltage and 0 on the current. Then we've got 0.1 on the voltage and 0 on the current. 0.2 on the voltage, 0. 0.3, 0. 0.4, 0. 0.52, 0.68, 0.7, 33, so we're jumping, and 0.8, 140. Oh, it's going to be difficult to draw this line of best fit. I'm going to really struggle on the iPad. State the name of component X. Now hopefully you're familiar with the various voltage current graphs for different components. Hopefully you're realising that that's a diode because it only allows current to flow in one direction only. The diagram shows an electric circuit. When the thermistor is in hot water, its resistance is 490 ohms. Show that the resistance of the fixed resistor is about 400 ohms. So we know we've got to find resistance, which is voltage divided by current. Notice it's a series circuit, which means that these two components' resistance will add up to the total resistance of the circuit. So what we're going to do is find out the total resistance and then minus the thermistor's resistance to find this component's resistance. So the way we do that is, first of all, we take the voltage, which we've been told is 6 volts. The current is 6.8 milliamps, so we need to divide that by 1,000 to get it into amps, our standard unit. So that looks like that. So we're going to pop that in here, pop it into your calculator, and you'll get a value of 882.35. And then to find the fixed resistor's resistance, we do that number minus the resistance of the thermistor, which is 392 ohms, which is approximately 400. So I know I've got the answer right here. Quite a lot of working to do there, but it is worth 5 marks. Explain how the voltage across the fixed resistor changes when the hot water is replaced with cold water. So in order to understand this, we need to understand how temperature affects the thermistor. Remember that as temperature decreases, as is this situation, the resistance of the thermistor increases. You need to learn that. Now, with increased resistance, it means that the current through the whole circuit decreases, meaning that there's a lower voltage in the fixed resistor, which is what we're being asked about.
This question is about Io, a moon of Jupiter. The diagram shows 2 jets of gas from volcanoes on Io. One jet of gas is from the volcano Prometheus, and the other is from the volcano Vashtar. Gas particles in the Prometheus jet leave the surface of Io and move vertically upwards. The particles reach their maximum height when their speed is 0. Some particles in the Prometheus jet reach a maximum height of 92 kilometers. Calculate the initial speed of these particles as they leave the surface of Io. And here's our acceleration. So this is going to be SwH, and the equation you need here is v squared equals u squared plus 2as. Let's make a note of what these letters stand for. So v is final speed, which we know from the question is 0. U is the initial speed, which is what we're after. Now in terms of the acceleration, it's actually going to be minus 1.8, and that's due to the direction in which the particles are moving. S stands for distance, which we've been told is 92 kilometers. Check the units. The units are in meters per second, so we need to convert 92 kilometers to meters by timesing by 1,000. So we're ready to get going. So our final speed is 0. We're after our initial speed. We're doing 2 lots of acceleration, which is minus 1.8, times the distance. Sort out that right-hand side to get minus 331,200. To get u squared by itself, you want to add that number to both sides. So u squared equals this, and then to get u by itself, you want to square root that number. And to 3 significant figures, the answer is 575 meters per second. Before the gas particles leave the surface of Io, they are trapped in a chamber. Explain how the gas particles exert a pressure on the walls of the chamber. Well, firstly, the gas particles must collide with the walls of the chamber. This generates a force on the walls. This is one of those perfect answers that's in my revision guide. And then what is pressure? Well, remember our formula triangle that I wrote up above. It looks like this. Pressure equals force over area. The Vashtar chamber has the same volume as the Prometheus chamber and contains the same number of molecules of the same type of gas. The temperature of the gas in the Prometheus chamber is 1200 Kelvin. The temperature of the gas in the Vashtar chamber is 1600 Kelvin. The pressure of the gas in the Prometheus chamber is 8.2 kPa. Calculate the pressure of the Vashtar chamber. So the equation we're after here is P1 over T1 equals P2 over T2. Let's label all these numbers just to make sure we're putting them all in the right place. Let's call Prometheus number 1. Let's call Vashtar number 2. So that this is therefore going to be T1, T2, P1, P2. The units are okay because we're in kPa still. So P1 is 8.2. T1 is 1200, P2 is what we're after, and T2 is 1600. So multiply both sides by 1600 to get x by itself. So that becomes 10.9. Explain why the pressure inside the chambers increases when the temperature increases. Use ideas about particles in your answer. So when the temperature increases, the particles have more kinetic energy, so they collide with the walls both more frequently but also much harder, which means that the force increases, and again, according to that equation, therefore pressure will be greater. So increasing the temperature increases the kinetic energy of the particles. The particles collide with the walls more frequently. And with greater force. And we'll state that equation again. Always state an equation as part of your physics explanation if possible. Explain why the particles from the Vashtar chamber reach a greater maximum height than the particles from the Prometheus chamber. Well, we can see from this calculation that the Vashtar chamber has a greater pressure of 10.9 versus Prometheus's 8.2. And therefore, by definition, this means that the particles in the Vashtar particles will have more speed, greater kinetic energy, and therefore will reach a greater height. So the Vashtar particles have greater gravitational potential energy due to the higher height they achieve. This question is about atmospheric optical illusions. A mirage is an optical illusion formed due to total internal reflection of light from the sky at the boundary between cold air and hot air. Diagram shows how a mirage is formed. State the formula linking critical angle and refractive index. Well, that's sine c equals 1 over n. The critical angle of the cold air at the boundary is 88.5 degrees. Calculate the refractive index of the cold air. Give your answer to 5 significant figures. So sine 88.5 equals 1 over n, which is what we're after. So to find n, do cross multiplication, which looks like this. So this number is a long number in your calculator. So to 5 sig fig, there's number 1, 2, 3, 4, 5. So the answer is this. Diagram 2 shows a ray of light from the sun. The refractive index of the atmosphere is greater than the refractive index of space. Complete the diagram by drawing the path of the ray of light through the atmosphere. So although this looks complicated, let's use a context that you're familiar with in class, which is air to a glass block. I'm going to quickly draw a normal. So here's our incident ray. And then remember, as it enters something with a higher refractive index, such as the glass block or the atmosphere in this case, it bends towards normal, which looks like that. So we just need to show that taking place here. So the ray would usually carry on here if it wasn't changing material. It needs to bend towards the normal. Diagram 3 shows a ray of light from the sun where the sun is directly overhead. Explain why the ray of light does not change direction when it enters the atmosphere. Again, this is very similar to the glass block experiment when you have a semicircle. And if you shine the light at 90 degrees, so in the same direction as the normal, it means that the angle of incidence is 0, which means there can't be any angle of refraction. Ray is travelling along the normal, meaning that the angle of incidence is 0. So the angle of refraction must also be 0. Explain why the wavelength of the light reduces when it enters the atmosphere. Now let's use this equation to help us, which is the wave equation. For the wavelength to reduce, remember that the frequency of the light wave can't change, so what must be happening to the speed? Well, you can use some numbers to prove this, but the speed must be also decreasing. So according to the wave equation, for the wavelength to reduce, the wave speed must have decreased whilst its frequency has remained the same. Suggest why the sun appears not to be circular when it is close to the horizon at sunset. Ooh, this is a real apply question. So if you think about the sun being very close to the horizon, it must mean that the amount of refraction taking place must be huge, and obviously refraction alters the direction of the light ray, so it won't appear circular anymore. This question is about the radio powered by a person turning a handle. The radio has a battery which stores energy when the handle is turned. The diagram shows the part of the radio called the generator. The generator produces a voltage which does electrical work on the battery. Explain how a generator produces a voltage. So remember, it's all to do with field lines being cut. So turning the handle makes the coil within the magnets rotate, and that coil cuts through the magnetic field lines of the permanent magnet. Really worth learning this answer off by heart. The radio receives a radio frequency of 93 megahertz. State the formula linking speed, frequency and wavelength of a wave. Cool, we just did that. Calculate the wavelength of the radio wave. So we know the speed is 3 times 10 to the 8 equals the frequency, which is 93. We need to convert this number to hertz by adding 6 zeros. Times what we're looking for, which is the wavelength. So do 3 times 10 to the 8 divided by that massive number to get 3.23 to 3 significant figures. The signal received by the radio is converted into an alternating current signal. Describe how the loudspeaker in the radio converts the alternating current signal into a sound wave. We need to touch on the motor effect. So we've generated a current. So at this point we have both a current and we have a magnetic field. And then according to Fleming's left-hand rule, that then generates a force, and that force is essential because it moves the speaker cone up, and then because it's an alternating current, the force changes direction, so it moves back down, and at that point you've got the speaker cone vibrating up and down, which is what's going to produce the sound wave. So we're going to start by saying that the loudspeaker coil has both a current and a magnetic field. According to Fleming's left-hand rule, this produces a force. The force causes the speaker cone to move up, and then the alternating current switches the direction of the force, causing the speaker cone to move down. State a modification that would increase the force on the speaker coil. Well, you could increase the strength of the magnet or use a larger current, and that's all due to Fleming's left-hand rule. Technetium-98 and technetium-99 are isotopes of the element technetium. Describe the difference between the nuclei of technetium-98 and technetium-99. Well, they're isotopes, so you want to state your definition here, really. Both have the same number of protons. Remember, these are found in the nucleus, but a different number of neutrons. And be really specific what that difference is in the number of neutrons. Technetium-99 has one more neutron. Technetium-99 is formed when the element molybdenum-99 decays. Complete the nuclear equation for the decay of molybdenum into technetium-99. Cool, we can see we're dealing with beta. So remember, in this case, a neutron turns into a proton and stays within the nucleus. So we'll have no change in mass number, good, but the proton number will increase by 1. Describe an experiment that a scientist could use to demonstrate that the emission from technetium-99 is gamma radiation. Include details of this safety precaution in your answer. So we're going to have to use a way of detecting radiation, which is going to be using a Geiger-Müller tube or a Geiger-Müller counter. Remember, we need to first of all discern the background radiation, so we can then take that away from the final answer. And then never forget to say that you want to repeat the readings in order to obtain a mean and discount any anomalies. Because it's worth 5 marks and we are dealing with radiation, we definitely want to point out safety concerns, so minimising exposure time, wearing a lead apron. So let's just get going. So here we are using a Geiger-Müller tube to measure the background radiation, then measure the count rate using the source. Subtract background radiation for true count rate of source. Repeat and calculate an average. Minimize exposure time and wear a lead apron. Plenty of points for our 5 marks. A scientist measures the count rate at different distances from the technetium source. The graph shows how the count rate changes with distance from the technetium source. The scientist suggests that the relationship between the count rate and distance is distance squared times count rate equals constant. Use data from the graph to determine whether these results support the relationship. Okay, let's pick 2 points and see what comes out of comparing them. So let's call that A. So the distance here is 1.3 squared times the count rate, which is 60, to get 101.4. Let's pick a second point B. Distance is 4 squared times the count rate, which is 6. Okay, now you have to use your common sense as to whether you think that these numbers here are similar enough to say that this relationship is supported, and I think that they are. There are actual statistical tests you can carry out, but that's overkill here. So you want to say 96 is approximately equal to 101.4, so the relationship is supported. This question is about satellites and their orbits. State a difference between an artificial satellite's orbit and a planet's orbit. Well, a planet orbits the sun, whereas the artificial satellite orbits the planet. State a similarity between an artificial satellite's orbit and a moon's orbit. They both orbit a planet. Kalpana 1 was an artificial satellite used to monitor the weather. The diagram shows the orbit of the satellite. Kalpana 1 has an orbital speed of 3.1 kilometers per second and completes one orbit in 24 hours. Calculate the height of Kalpana's orbit above the Earth's surface. The radius of the Earth is this. So effectively, we need to use this equation, which is for calculating orbital speed, because we're after r, the orbital radius. Just checking our units, cool. Our kilometers are fine. So our unit is kilometers, so we can keep 3.1 in kilometers. That's great. So 3.1 equals 2 pi r, which is what we're after, over the time period. Be careful with your time period. We've got seconds and hours here. So let's convert 24 hours to seconds. So convert into minutes by timesing by 60, and then into seconds by timesing by 60 to get 86,400. So times both sides by 86,400. and then divide both sides by 2 pi to find r, which is 42,628. Now be careful, because that r value you've just calculated is this distance here, but we know that the radius of the Earth is 6,400, so we need to minus that number to get the true value, which to 3 sig fig is 36200. The Doppler effect occurs when there is relative motion between the source of waves and the observer of the waves. Explain how the Doppler effect causes a change in the observed frequency of the waves. Again, we're using this equation. Now, say with the Doppler effect the source is moving away from us. It means that the wavelength goes from that, for example, to being much longer. So our wavelength here has increased. The speed stays the same. So what does that do to our frequency? Well, it decreases it. So as the object moves away, its speed remains constant, but wavelength increases, meaning that the frequency decreases. And remember, this is all according to this equation, which you want to pop in there for your final mark. Suggest why the radio waves from Kalpana 1 detected on the Earth's surface are not affected by the Doppler effect. Well, this is because the distance of the satellite Kalpana from the Earth does not change, meaning that we get no change in wavelength or frequency.